Hello and welcome back to Statistics1. So we are starting chapter 6, introduction to normally distributed, not values, variables. Now I have to fix this. Hold on. Give me an hour. Values? No. There we go. Variables. Much better. All right. So we start with the concept of a density curve, and we have seen these curves, distribution curves, in chapter 2, I believe, for the first time, and we had the reverse J shape, and we had the bell shape, and skewed left and skewed right. And then all of the different distributions. We are going to focus on this chapter only on the bell-shaped curve, but in general, all of these curves are called density curves. They come from the frequency distribution, right? And these density curves will have area under them. So if we take a look, can anyone tell me, you remember which one was this? Well, this is shorter than that, right? So it's right skewed. Yes, good. So this one will be right skewed. And something like this, right, including all other ones, will be called a density curve with two properties. Density curve is always on or above horizontal axis. So density curve is on or above horizontal axis. And number 2, total area under the density curve equals 1. Now this one will eventually become your 100% probability. So what we are going to do next is understand that for any density curve, you can literally draw whatever you want. If I'm going to have a single z value, I'll have area to the left, area to the right, or z1, z2, area in between. So these are the 3 cases which we are going to examine. And as I mentioned, there will be some chart involved that you will look into, because this is not calculus-based statistics. Calculus students would get to calculate those numbers. So now, the one that we care about and focus on is normal curve and normally distributed variable. Normal curve, also known as bell-shaped curve is the one that would look like this. So practice to draw this as symmetric as possible. Now area under this is equal to 1. So area equals to 1. Area under the curve. And that represents 100% of all observations that we had for this variable. We have the definition for normally distributed variable. A variable is said to be a normally distributed variable or to have a normal distribution if its distribution has a shape of a normal curve. So normally distributed variable. So what would this be? Pick any of the genders, doesn't matter which one, and just say height. Right? It's normally distributed. IQ, normally distributed. Shoe size, normally distributed. So pretty much everything that we could think of would be normally distributed, which is why you could possibly cheat on a test with that. If you have an exam that has 80 questions, multiple choice or something, right, 60 questions, if they're normally distributed, right, at that many questions, you would have approximately the same number of A's, B's, C's, and D's as answer. So if you answer everything you know, right, then you count which letter was circled the least amount, and everything that it's not done and you have no clue, circle that letter. It works wonders, right? Because those exams, if you have a multiple choice exam of 60 questions, it's pointless, and the course is probably pointless too, along with it. So you might as well make sure that you pass it on the first shot. So, yeah, I know, right? So we have a variable for normal distribution, and we end up with having this. So I would like to, one more time, go on the website and show the distribution of IQ, right? So let's go and say IQ. IQComparisonSite.com, and they show here that the IQ is normally distributed with a bell-shaped curve, exactly, and it shows standard deviation of 15, with 100 being the middle. Now, lately, we are noticing that the actual mean of the IQ is actually shifting. So this might be, you know, outdated now, but what you see is we see our z-scores here, and then we see the standard IQ scales, and you see the scale that has a standard deviation of 15 and the standard deviation of 16. Now that's all open to interpretation, which one should be the one that we use, but what you see is that vast majority of people are the IQ scale of 85 to 115, and we saw that earlier with that empirical rule and stuff that we learned earlier. That was about 65% of all people fall in that category. And then we have the first standard deviation right between 1 and 2, 115 to 130, which are higher, right, IQs. And then after 130, genius, we remember that Stephen Hawking was clocking 160 on this scale. 85, that's already borderline deficiency to actually do a task. Military will not employ anyone with the IQ less than 83. Now, if military is not employing you, right, then pretty much that's a shot for everything else. So technically below first standard deviation is everything that is on the welfare immediately. So normal distribution, and this is something that involves all people, right? It's not 7, people sitting in a classroom and say, this is our distribution. No, this is across the population. So we would say that IQ is a normally distributed variable because its distribution is a bell-shaped curve. If you don't know what IQ is, it's the intelligence quotient, right? Measures the intelligence. By the way, your math exams and your math scores do not measure intelligence. If you want to know, you take the IQ test, right? You don't get to weigh with 100 in math and say that you're smart. Sorry. Okay. So an example would be IQ, and we're going to draw bell-shaped curve with a mean of 100, and then 115, 130, 145 on the right-hand side, and 85, 70, and 55 on the left. And those would actually be the IQ points, which we can call X. Now, wherever the mean is, there will be a 0, and then 1, 2, 3, -1, -2, -3, as standard deviations. These things would be your z-scores. So we will be calculating the z-score for a particular IQ, and we would know approximately the percent of people that are below or above that particular IQ. Now, there are also job, like IQ is a predictor of what job you would be successfully doing, and you can take a look at that scale. I'm not sure where I read that, but let me see. Average IQ by occupation, right? Is that the one? I think this is a joke. Let me see. Oh, no, these people are trolling. Yeah. No, it was a troll website. Free IQ test for the employment. I don't know. I found it somewhere. So I found that, if I remember well, office type jobs, like support jobs, secretary, let's say, assistant of some kind, would be anywhere from 95 to 100. Police officers at 105, detectives over 110, right, and so on. So there are predictors, right, between jobs and so on. Anyway, now what else do we need to take a look at? I already said that this is going to be your mu, which is your mean, and then you have mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and on the other side, mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma for standard deviations. I already said that you are looking into tying the number of the area under the curve to probability and to percent. So if the total area under the curve is 1, if you make a cut somewhere, each one of these pieces will be less than 1, so it will be 0.63, right, or 0.18, and clearly those would be 63%, 18%, and so on, right, with the probability to find what you want. So these problems will be worked on later. I just want to give a quick example the way this works. What percent of population has IQ less than, give me a number, 130. Thank you. So we would use the z-score formula to first create a z-score, and then we'll use the chart to look at it. So x minus mu divided by standard deviation sigma. In our case, we have x, which is the 130, minus the mean of 100, divided by 15, which is standard deviation for IQs. And we have 30 divided by 15, which is 2. So z-score is equal to 2. Now, you will go to a z-score chart, and that will tell you the percentage to the left. So you can open the z-score chart or table on your phone, or you can just look at the back of the book. You already have it. Beautiful. Let me just show that to the masses over here. They would look like this in your textbook. It's just chart with endless amount of numbers inside. Your z-scores will be given on the edge, and z-scores on the edge, and areas are in the middle. So you will locate your number 2. This is negative, it's positive, right? So you will locate number 2 and you will find the value. So I'm just going to pick one of these tables. Usually they also have a drawing like this showing that this table only gives you area to the left. If you want area to the right, we'll learn common sense 1 minus the area to the left. But let's just pick a chart. They all have the same numbers, same values. And at this point, I'm not sure if you can see this, so I'm going to go Control plus. Z-scores, we will have an entire lecture on learning how to use this. I'm just going to go and say we don't have any decimals, so it's going to be 0, 0. This is a decimal 1, 2, 3, 4. So the first digit and the first decimal and the second decimal. So that's how this whole thing organized. Here is your 2. So this gives you the area of 0.9773, meaning that 97.73% of population, right? 97.70, that's almost 98% of people on the planet have the IQ of 97, which actually makes sense because, right, 1% of people that actually create industries and make those fortunes, right? It totally makes sense to have this as a number. Yes?
They have an IQ of 97, or there's 97% that's less than
130, yes. So 97% of people, 98% of people, of all of us here and outside the next room, and the next town and the next country, 98% of all people on planet have IQ less than 130. That's the. So this is what we are going to do with these normally distributed variables. I don't have to talk about IQ. I can talk about the height. I can talk about the weight. Well, the weight is heavily skewed to the left in US, but if you take a look at the rest of the world, and then you have the mean age and technically anything, right? Anything you can look at these things. So the formula that we are going to use to transform your variable x into a z-score is the z-score formula you learned in chapter 3. It is still relevant. This is the formula. This is sigma, standard deviation, right? So this formula is going to be utilized pretty much all the time. For your project, you might pick 1 or 2 or 10 values of data that you collected and then run z-scores and, for that, arrange it maybe in a table, talk about values and highlights and data and something like that. So this is called a z-score. And the z-score, if you remember from chapter 3, measures the distance. Measures the distance in standard deviations away from the mean. It's also standardized variable because most of the data points, 99.7 if you remember, will be between the 3 standard deviations to the left and to the right. So it's very rare to venture outside of those. Now we saw that Stephen Hawking IQ of 160 is 4 standard deviation away from the mean, right? and let's take a look at some of the homework. This is it in terms of lecture. Oh, by the way, just to make sure for this problem, I draw a small sketch over here. I'll put here. So this is 130 IQ on X, and it's 2 on Z. It's the same value, okay? So I read the scale. Either as IQs, in which case I have 130, or I read the scale as Z-scores, which is 2. It's the same value. And the area that we were considering was area to the left, because I wanted to know the percent, right, of people that have IQ less than 130. So this over here is about 98%. That means that only about 2% of human population has the IQ higher than 130, because we have to have 100% under the curve. So if 98% is to the left, then 2% has to be on the right. And this is what the entire chapter will be concerned with, these kind of calculations. Now you can, right, since we already learned over here, you can ask a question, well, what is the amount of people that are between 100 and 110, right, and so on. So you can, I'm sorry?
Based on the first answer of 130.
No, nothing completely independent.
Also, this is separate.
Yep. Well, it's not in the first section, so we'll deal with that when we get there. I think it's next class. So let's take a look at some of the basic ideas. Some of the very simple questions just to check the concept, like 611. It says, given that 28.4% of all possible observations are less than 11, of all possible observations are less than 11, determine the area part A to the left and part B to the right. This is a question which only is checking your ability to pay attention to words. I said that probability is equivalent to area, which means the answer for the part A is what? 0.28, yes, 0.284. So area under the curve must be less than 1. It has to be between 0 and 1. And you can either express it as a percent, which in turn you're talking about probability, or you can express it as a decimal, in which case you're talking about the area. They're both the same, right? Now, if we have 0.284 to the left, then you have 1 minus 0.284 to the right, which is 0.716. And if you want to draw this distribution, you draw the shape 0.284. That has to be somewhere here, because you need to have more beef over here, right? 70 over 70% on the right and less than 30% on the left. So this is your 0.284 and this is your 0.716, and this will be your number 11 on the X scale. I cannot transform this into a Z because I do not have information on the mean and standard deviation sigma, so I can't do anything else other than do this. Sketch the, so this is 623. Sketch the normal distribution with mu equals 1 and sigma equals 3. So we have a normal distribution. We know we are supposed to put a bell-shaped curve. We know that the middle where the peak is your mean, which is going to be 1. And now we have two scales to worry about. We have 1, 2, 3 standard deviations on one side. Each time you add a standard deviation, so it's plus 3, so 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10. And then keep subtracting on the other side. So 1 minus 3 is negative 2, then negative 5, and negative 8. And these would be your x's. Now your z's are always 0 where the mean is 1, 2, 3, and then negatives. Negative 1, negative 2, negative 3 on the other side. Without a fail. Every time is the same. And I believe I'm just going to quickly peek into, yes, the next section, which we are going to cover on Monday, will teach you in detail how to read the chart and how to calculate areas and connect to probabilities and things like that. What I need you to do is to walk in with a chart, right? Otherwise, you'll be sitting in class like a bump on a lot. So either bring the textbook, bring the device that you can go on MyMATLAB and open the textbook and look at the z-score. Go online and find the z-score chart and print out. Just make sure that you have some form of the z-chart next class. Because for the rest of the semester, which is another month out, we will be using that chart and then eventually also t-chart, t-score chart, every class. And those will also be provided to you on the exam because you can't do anything without this. So make sure you have a form of a z-chart next class on Monday so we can operate. See you Monday.